Welcome back. Our second speaker today is Stefano Albrecht, and a postdoctoral fellow at the University of Texas at Austin, and in the Department of Computer Science and Engineering. And Stefano works on the theory and practice of autonomous agents and multi-agent systems, especially talking about agent modeling and belief modeling. So he's here to talk to us today about practical and theoretical progress on model updating in multi-agent systems. So join me in welcoming Stefano.
Thank you very much. I should point out that this work is supported by a research fellowship from the Humboldt Foundation, just to have that covered as well. So this talk's entitled Learning to Distinguish Between Belief and Truth. I realized that there has been a lot of work in the philosophy and psychology communities about what it means to be true and have beliefs. I just thought this would make for a compelling title, but I'm not going into the differences between the two things. I'm hoping it gets approximately clear as I go through the talk. Okay, so it consists of 3 parts. Yeah, you can't see the pointer, can you? Not really. So I'm just going to use my hand instead. So it consists of 3 parts. In the first part, I will explain to you what I mean by the title and the problem that we consider here. In the second part, I will tell you about some research we did to address one specific aspect of this bigger picture problem. And in the third and final part, I will give you a brief description of a possible future and a research agenda. Okay, introduction. So this talk is about multi-agent systems. Such a system consists of a collective of decision-making agents. Each agent can take certain actions, such as A, B, and C, and each agent is trying to accomplish certain goals, such as reaching a goal state in the environment and maximizing a given utility function. And what makes the system interesting and often very challenging is the fact that what one agent should do can depend critically on what the other agents are doing in the system. Agents often have to deal with a variety of uncertainties. They may be uncertain about the state of the environment, and they may also be uncertain about the actions that other agents took in the past. And importantly, they may be uncertain about the behavior of other agents. And by behavior, I mean the way in which an agent chooses actions based on the available information. Now, all of these are important issues, and there has been a lot of research, but in this talk, I will be focusing on uncertainty about behaviors. Okay, so there's basically 2 ways in which you can address that. There's what could be called model-free methods, and that includes regret minimization, policy gradient ascent, model-free reinforcement learning, and various other approaches. These methods do not directly address the uncertainty about behavior. What they do is they use the information that they observe during the interaction and try to manipulate their own behavior directly. So, there's no man in the middle. The other approach could be described as model-based methods. And these methods basically try to learn models about the behavior of other agents based on the interaction history. And there are many ways in which you can do this. You could try and fit decision trees, neural networks, finite state machines, and various other methods, case-based reasoning, graphical methods. And then the idea is to use that model, the resulting model, to inform your own policy, to plan your own actions. I think there are some important features that the model-based approach provides. And basically why you would want to try and model an agent is because the hope is that some of the observations that you encode in your model will generalize usefully to other unseen situations. And what this gives you, well, it allows you to plan into the future. That's the key part. It allows you to perform guided exploration, for example, and it can also be used to do things such as risk control and aversion. And all of these things are hard to do if you don't have a model to begin with. This is useful, but all of these methods lack one key component currently, which is that they provide no notion of model criticism. So in other words, they produce models, but they don't check the validity of the resulting model during the interaction. And so what can happen is that an agent using these methods can end up learning and using a model without ever realizing that it's incorrect. And that's an important disadvantage. So here's a simple example, a very simple example. Let's say a robot plays rock, paper, scissors against a human. I assume standard rules and standard payoffs. And let's say the human plays a very simple sequence of rock, paper, scissors, and so forth. Now, the robot doesn't know how the human behaves, but it can try to learn about the behavior. And in this simple example, the robot is fitting a model based on the assumption that the human is using a fixed distribution over actions, or fictitious play as it's known in the community. So if you use the empirical frequency to fit the parameters in the model, then in the limit you end up with a uniform distribution, which is incorrect, of course, because really the human is using a deterministic sequence. In the planning, if you were to plan with the correct model, your expected payoff would be 1, because you can always choose the correct or the winning action in each time step. Whereas planning with the learned model would be, the expected payoff would be 0, which is as bad as playing randomly. And the problem here is that the robot will never realize that the model is incorrect, neither in the learning step nor in the planning step. And this is a very simple example, but it also holds for more complicated model fitting methods. And this is a very simple example, but it's not all that hard to scale this up to more realistic and complex examples, such as elderly support, user interfaces, or I should say adaptive user interfaces, and electronic markets. And we had a really interesting talk already about that. Essentially, any domain where you have a collective of agents that need to interact closely with each other and that have to develop some kind of understanding of each other's behaviors. What can go wrong? Well, in principle, anything. Agents attempt to learn models that end up being incorrect. Incorrect models can make incorrect predictions, and incorrect predictions can lead to bad actions. So if in 50 years from now I still happen to be alive, and we're at a technological stage where a robot like this can carry me around my home, I would hope that if it attempts to learn about my behavior, it has some reasoning capability to make sure that what it learns makes sense, rather than dropping me on the ground and killing me in the process. So it's about safe and robust AI in that sense. So what's the problem here? Well, the fact is that the model is effectively a hypothesis, or loosely speaking, a belief of the agent. And hypotheses can be false. It's a key part of the definition. But the problem is that the models are not treated as hypotheses in these methods. And so the fact that they can be falsified is not even contemplated or considered in the first place. You might say that you can address this problem or alleviate it, at least to some extent, by maintaining multiple models. And then you can do some model selection over your models, such as keeping beliefs. But that doesn't correspond to model criticism. And in this particular example of maintaining beliefs, well, the problem is that the beliefs quantify a relative likelihood, but they never quantify an absolute truth. And so even if all your beliefs point to one model, that model can still almost arbitrarily be incorrect. Okay, so here's I think what we need to do, or what agents should be able to do. They should be able to construct hypotheses of behaviors, but they should also be able to contemplate the truth of the hypothesis. Both of these things should go hand in hand, and that's currently not the case. What can this do for us? Well, in the first place, agents can decide to reject a model. And then depending on how this reasoning is being carried out, the agent may decide to change, for example, some of the assumptions underlying the model, such as what information to feed into the learning process, or perhaps the structure of the model and the parameters in the structure. And all this is done in the hopes of obtaining a better model ultimately. Or alternatively, if none of these steps seem to help, after rejecting a model, well, at the very least, the agent should be able to resort to, or be able to decide to resort to some safe policy that can work without a accurate model. And in the setting of game theory, for example, this could correspond to a maximum strategy that can guarantee a certain minimum level of performance. So, safe in that sense. Okay, so that's the introduction. That was a brief description of the problem and the direction in which we're going with this. And in the second part, I will tell you about some research we did on a very specific aspect of this bigger picture problem. And it's what we call behavioral hypothesis testing. This was first published in the UII conference last year in the Netherlands, and it's been published more recently as part of a more substantial manuscript in the artificial intelligence community. So if you decide to take a look and you have some comments, please do get in touch with us. Okay, let's make it more concrete. So the model is an hypothesis because it's either true or false, and because it's testable, importantly. This is the key definition of an hypothesis. And then the natural question that you can ask yourself is, well, if I interact with some agent J and I have a behavior, an hypothesis for the behavior of that particular agent, and also giving a interaction history, does that agent truly behave according to my hypothesis about the behavior? It's something that you can ask yourself and that an agent should probably ask itself as well. Well, here's an example to make it more concrete. This table shows the first time steps of an interaction process between two agents playing the rock, paper, scissors game, such as the robot and the human that we talked about earlier. In the first column, you see the time steps, 1, 2, all the way to 5. In the second column, you get the actions taken by the agents in the respective time step. So rock and paper, for example, in the first time step. And the third column corresponds to the hypothesis that agent 1 maintains about the behavior of agent 2. So, for example, in the first time step, agent 2 chose to play paper, and agent 1's hypothesis would be that agent 2 plays paper with probability 0.1. And this goes on in the same way, and the hypothesis can produce these probabilities based on the prior interaction history. So you can think of the hypothesis as some kind of a black box program that can take as input the interaction history and produces probabilities.
So I guess you should not have zero there. This is like a Bayesian update.
This isn't a belief, it's just a distribution over action outcomes for agent 2. So there can be a zero here because this sums up to 1. It just means that the hypothesis does not believe that agent 2 would choose a rock in this time step with any chance.
So it is like certain about this fact. So like if it had either some prior, there was a data with prior, should never have become certain. But it doesn't mean that
the belief model doesn't have to be Bayesian updating.
Yeah, this doesn't have to be. So as I just said, just think of this policy as some kind of a black box function. It takes as input the interaction history, and it does some internal logic and reasoning and produces this. Okay, so the question is, how should agent 1 decide whether or not to reject the hypothesis about agent 2? And importantly, all of the actions that you see in the column here of agent 2 are supported by the hypothesis because they're in the positive mass. So you can't just outright reject the hypothesis. Now, one way to address this, or a natural way, would be to compute some kind of score from the information given in the table. And one example is the empirical frequency distribution. And while this is relatively simple and appealing, there are also two big issues. One is that the question of when your scoring scheme is sufficient. By sufficient, I mean, when do you know that it's sufficiently informative and discriminative enough for you, in order for you to make this decision? If you take the empirical frequency and go back to this example, well, then you can tell immediately that it's not sufficient because the distributions change drastically in all the time steps. And so you can't just take the average of your predictions. And then the second issue is, well, once you have a scoring scheme, then you will have to find some threshold parameter beyond which you decide to reject or not reject. And this would depend highly on the scoring scheme that you choose, but it doesn't necessarily tell you how you should choose the parameter. And furthermore, once you change your scoring scheme, you will probably have to change the parameter as well because the semantics of the parameter change. So what we propose instead is a method that is based on frequentist hypothesis testing, or a p-value calculation, which I'm assuming most people will be familiar with already. This has two interesting advantages. First of all, it allows you to combine multiple scores into a common test statistic. And this is done in the hopes of obtaining an overall more reliable and robust test statistic or scoring metric. And the second is that in this particular method, the decision threshold parameter would correspond to the significance level, which is, you will all be aware of this already if you do p-value calculation. And an interesting fact about the alpha parameter is that it's, in a sense, defines a uniform semantics of what rejection means. And it's invariant of the specific scoring scheme. So even if you decide to add or remove certain scores from the overall metric, it doesn't change the semantics of the decision threshold. There's also other advantages, which is, for example, this can be implemented quite easily and is very efficient in practice, but I'm not going to talk about this in this talk here. Okay, before I go into the method description, here's just some simple notation. This won't be heavy math, but there's some minimum notation just to make sure that you can follow the exposition here. So we say that an agent I has a behavior denoted by pi I, and pi I is basically just a black box function that takes as input the interaction history. The history itself can contain all past states and join actions and the current state, and then it produces a distribution over actions available to that agent. So in other words, a hypothesis is defined as a mapping from histories to distributions over actions. Okay, so here's the key idea underlying the model. We control one agent I, and we observe another agent J. Pi j is the true behavior of agent J, and pi j star is the hypothesized behavior. And the question in the testing problem is, are these two things the same? Well, we can't answer this question directly because we don't know the true behavior. We only have the hypothesis, but we don't know the true behavior. But here's what we can do instead. First of all, we know the past actions of the other agent because we can observe the history. So we can observe that vector of actions, and we know that that vector was generated by the true behavior. And in addition, we can use our hypothesized behavior to generate a similar vector of the same structure, and this corresponds to a vector of hypothesized actions, assuming that the agent truly uses that behavior. And then once we have these two vectors of actions, we can address the original question as a two-sample problem, which is the question of whether these two vectors were generated by the same stochastic process, which in this case is our hypothesized behavior. So that's the simple idea underlying this whole method. So we want to compute p-values. This is not new. None of this, what you see here, is new. But let me just explain what it means anyway. This here is the test statistic that we calculate given the two vectors of actions that I just explained to you. So this is the vector of observed actions, and this is the vector of hypothesized actions using our hypothesis. And then this is just the test statistic. Now, the p-value itself is just the probability with which we expect to observe a test statistic, at least as extreme as the one that we've just calculated. So none of this is new. This is all of this should be familiar already. This assumes that the hypothesis is true, and that allows us to use the same distribution. And what we then do is, well, once we have the p-value, we decide to reject the hypothesis if the p-value is below some manually chosen decision threshold. So this is not new here. None of this is new. Here's how we do the test statistic, and that's where it gets more interesting. On the top level here, the test statistic for two vectors of actions is defined as the mean of the tau prefix test statistics. That's what the tau means here. So the tau here means that we just take the first tau time steps of the overall vector of actions. So if you have, for example, 10 actions, and you take if tau is 5, you take the 5 initial segment. That itself is defined simply as the weighted average of scores calculated for these tau prefix vectors. So W refers to a weight. It could, for example, be uniform, and the ZK refers to a specific score function. And one score function could be the empirical frequency distribution, but I'm going to go into some examples in the next slide. The intuition is this: the score function intuitively could correspond to something like as a likelihood. The likelihood that our hypothesis would produce the vector that we give to this function. It doesn't have to be a likelihood in a strict theoretical sense, but it's useful to understand the method, I find, and that's why I like to use that when I explain the method. Okay, here's a very simple example of a score function, Z1. So if this is our hypothesis, and this is some input vector, it's simply defined as the average ratio of probabilities assigned to the observed actions in the vector and maximum probability actions in that respective time step. So this is the probability assigned to the observed action at that particular time step tau, and this is the maximum probability that any action receives at that particular time step. is very simple, and you can see already how this would translate into a likelihood. Intuitively would say that, the closer you get to the hypothesis, the more likely or the higher the score is and corresponds to a likelihood. But you can also see that this is highly imperfect. For example, if our hypothesis is a uniform distribution, then it doesn't matter what the true behavior is, the score will always be the highest score then. So it's imperfect in that sense as well. But I get back to this in a second. Here's another example, just skip over this, but it's similarly simple. And here's another example, quite simple too. This is based on the empirical frequency. Here we just take the average distribution of observed actions in the vector, and here we just take the average of all hypothesized distributions. And this whole expression just takes the overlap of these two things. And so again, you would think that, the greater the overlap between these two things, the more likely it is, in a sense, intuitively, that this generated this here. And you can also see, going back to the first one here, that this one isn't necessarily fooled by uniform distribution, such as this one. So the idea would be that we can somehow combine these two things to make an overall more informative test statistic. That's the idea here. They're all imperfect, but they can be combined to make up something stronger. Okay, this is just one last step, and then we finish with the method description. There's some interesting math you can do, or some interesting theory. You can show that the test statistic doesn't necessarily converge in the process, but you can show that the fluctuation is nonetheless normal in the limit. And this would tell us that we can just use a normal distribution to learn the test distribution. But there's an important problem here. If you use a normal distribution, it would fail to account for the skewing, the gradual skewing in the initial learning process. And you will find, for example, in the multi-agent setting, with the data in the first, say, 100 time steps, you get a highly skewed test statistic. So a t-distribution or a normal distribution would fail to capture that accurately. So we instead propose to use a skew normal distribution, which includes the normal as a special class and has some parameters. And in this work, we provide a learning method that can learn these things online during the interaction based on a sampling procedure. But it's not necessary for the rest of this talk here. So we basically learn the test statistic online as we interact. And here's some interesting experimental results. So in this first set of experiments, we assume that our own behavior, the behavior of the other agent, and our hypothesis for that other agent's behavior, they're all just random behaviors. And random behaviors here are defined as random distributions of actions at each time step, completely random. We tested all combinations of score functions, Z1, 2, and 3, which are the ones that I showed you earlier, the examples. And before you go ahead and interpret the data, let me just explain to you what the axes mean here. So the numbers here correspond to the combinations of score functions that we tested. So here we used 1, here we used 2, and here we combined all three of them together. And blue corresponds to the case in which the hypothesis is correct. So the correct decision here would be not to reject. Red corresponds to the case where the hypothesis is incorrect. So the correct decision here would be to reject. And obviously we want to be as high as possible here. So you can see these are some very good results. We have almost 100% in most of these cases, or bordering 100%. There's just one exception to this, which is the third scoring scheme, or score function. And there's a very simple explanation for that. The explanation is that the third score function is just no good for these kinds of behaviors here. If you recall, the third score function simply takes the overlap of the empirical average and the average of all hypothesized distributions. But for these particular behaviors, both of them in the limit will just be uniform distributions. So we will have no useful information from that score metric. And this explains why we have a good rate here, because in the limit, any two behaviors will always look the same to us. We will never reject, and which is good in the blue case. But it also explains this, because again, in the limit, any two behaviors will look the same to us, and then we never reject when we should be rejecting. But here's something cool about this method. We can solve that problem by combining any of the other two metrics, or adding it to the third metric. And this is what you see here. So the lines here correspond to the evolution of the p-values. And ideally, they should be converging to 0 in this case, because this corresponds to the red case when we should be rejecting. You can see that this is the case for all lines except for 3, which is the red one here. 3 simply is not a good score metric. But as soon as we add any of the other guys, you can see that convergence is restored or healed, in other words. And this is the case for these guys too. Oh, I should have pointed out, sorry, I forgot this. These 3 bars, the individual ones, correspond to a higher complexity in the interaction. So this is 2 actions, 10 actions, and 20 actions. And you can see the healing takes place in all complexity levels. And this is exactly the effect that we wanted to achieve with this. We didn't necessarily know ahead of time that this was going to be a bad score function, but we can combine this with other possibly imperfect score functions as well, and then we heal the convergence here.
Why does the combination of 2 and 3 heal a lot more slowly than the other combinations?
Right. So for this case here, you can see that it's almost as fast as the other ones. But for the higher complexity ones, it just turns out that it needs more data. The second score function, which I didn't explain, but it's relatively simple as well, just isn't quite as different from the third one as the other ones would be. So it just needs more data basically. What this means is, for these cases here, if we just add more time to the interaction, they gradually go up as well here. This is a cutoff after 10,000 time steps, which I thought would be sufficient for the learning process to have converged or something. But if you add this to maybe 20,000 time steps, this goes up gradually as well. And you can see that the convergence goes to 0 here. Okay, here's another set of experiments, in this case for adaptive behaviors. We have different kinds of adaptive classes. For example, co-evolved decision trees and co-evolved neural networks. I'm not going into the details here, but they're basically just behaviors that adapt to certain portions of the past interaction history. For example, the past 5 time steps. And here you can see that we have similarly good performance in the positive case, but we have a mixed picture in the negative case here. And in particular for this bar, which corresponds to the co-evolved decision trees. And what this does is, this shows you an important limitation of the testing method, which is that we only make decisions passively based on data that is provided to us by some external process. So in other words, this testing method does not probe specific aspects of the hypothesis. If this is the structure of the true behavior, a tree, and if our hypothesis is a tree as well of the same structure, and if it just so happens during the interaction that we only ever see this part of the tree, but the differences are only in this part of the tree, well, then there's no way for the method to make the right decision. So in other words, something else is needed. Testing is not the only thing that we need here. Okay, this was the second part. And in the third and final part, I will tell you about what I think could be an exciting future research agenda. So the future. So we saw that testing is an interesting and useful part, but it's also just a part of the bigger problem. As you just saw, it's not sufficient in some cases. I think what is needed eventually in the future is something that could be described as hypothesis contemplation. It's a much more holistic way to look at things. It's a reasoning process that truly considers models as hypotheses and not just as models that we run with nonetheless. So this would consist of elements such as being able to generate hypotheses. You could do a machine learning and fit models. You can do case-based reasoning, or you can make guesses based purely on the structure of the problem, such as equilibrium solutions. Then we would have an element that does selection. And this could, for example, be maintaining beliefs over a potentially promising subset of hypotheses. Then we have testing, which is what we just saw. Then we would need exploration and revision, which I'm going to talk about in just a minute. And then there's probably even things that I don't even include in the figure here. So what we really want an agent to be able to do is this practically, contemplate truly an hypothesis. But importantly, this is happening online. This is not an isolated process. This is online and happening during an interaction process. So really, it would probably look more like this eventually in the process. So here's some more details about exploration. Exploration is simply the question of how and when we should explore aspects of the hypothesis. If you remember in the last part of the second part, where I showed you that we didn't have good results for the rejection case, Well, the explanation was that we didn't actually probe this aspect of our hypothesis. We simply didn't see data coming from here. And this can be solved with exploration schemes. So in this case, we used a simple randomized exploration scheme. For example, epsilon greedy exploration, where you have a certain probability of randomization. And it shows that this goes up really quickly then if you do that, because with the randomization like that, you quickly end up in this part as well. But of course, you can't just do that in practice, because any of your actions will have an effect on the other agent, and you don't just want to do randomized action choices. You will have to be smarter than that. And that's, I think, a very interesting key problem that we will need to address. Something else that's really interesting, and something that I'm involved in currently as well, is revision. The question is, how should you revise and improve aspects of your hypothesis? So rather than generating new hypotheses from scratch, you already have something to begin with, and you want to revise certain bits and pieces based on what you see. So an example would be, if you assume, or if your hypothesis is that the other guy is a reinforcement learner, well, aspects could be the learning rate, the exploration rate, the discount rate, and various modules and parameters. And I'm assuming you're familiar with this. The question then is, based on what you see in the interaction, how should you revise and improve these things subsequently? And when should you do that as well? And then, so this is a really interesting but challenging question. Okay, so in summary, individual pieces of this whole puzzle exist. We have people in the community and people in this room who have worked on bits and pieces here. But what's missing is a complete integration of these individual pieces into a more comprehensive reasoning process. All of these things need to be put together, I think, eventually. I think this is an important problem because of the things that I just pointed out to you in the presentation. And it's feasible and timely precisely because we've worked on this for a while now. And also, I think this is relevant not just for multi-agent systems, but actually for the broader AI community. We all use models in various aspects of models, but we don't do autonomous model criticism. That's something you don't see much in the community. So if you're familiar with statistics, then you will probably be familiar with model criticism. They've worked on this for many decades. But there's a difference between that and AI. The difference is that in AI, we will need to carry this out autonomously. And that's, I think, where the leap has to be done. Okay, so this is the goal, but there are also challenges. Since we're combining various elements, there will be issues relating to complexity. We want this to be efficient. There will be issues relating to soundness and completeness. All of this will need to be worked out. But I think something more interesting is that sooner or later, when we pursue this goal, we will have to reconsider whether correctness is the right goal for this. And maybe we should contemplate something else, something that could be described as usefulness. Usefulness is something that could include correctness as one aspect, but could maybe trade it off with efficiency and model complexity. And the idea is that you can then carry out things such as estimating value of information and go beyond the correctness criterion. There's this famous citation in the statistics community by Box that goes something along the lines of all models are incorrect, but some models are useful. And maybe agents can learn to reason along those lines as well. And the last part, which I think could be really exciting and a really interesting step forward, is if agents can learn to carry out this hypothesis contemplation autonomously, rather than us crafting these individual pieces and then putting them together into an integrated solution. This is a more mechanistic approach, which is what you see a lot in AI. But I think it would be really interesting if we can just, not have these individual pieces, but let the agent learn these things autonomously. I think that could be a really interesting and tremendous milestone in the AI development history. Okay, that sums up the presentation. Thanks very much for your time, and I look forward to interesting discussions.
So, can I ask, so it seems that the things that you're doing, they look somewhat generic in the sense that you have some unknown environment and you have some hypothesis and you're trying to sort of find some statistical test for this hypothesis. So it was not so clear why the special relevance of multi-agent settings, because it seems that it is relevant to multi-agent settings equal and just to general unknown environment equal.
Yes. So first of all, this is not just not just about statistical tests. As I was trying to explain, the tests that will just be a small part of the bigger picture. And the reason why I'm relating this to multi-agent systems is because it's simply not happening in the multi-agent systems community. But I also pointed out in the presentation that this is relevant for many areas in AI. So if you do model-based reinforcement learning, this will translate into that as well. If you do database game theory analysis, you have models as well, and you will have to have some. If this is to be carried out autonomously by an intelligent machine, they will need the machine should be able to have some model criticism in the reasoning process. So so basically that's the answer to that. It is relevant to many things.
I'm wondering if this can be phrased as a form of anomaly detection as well. When you're looking at something outside of your class of models for how the other agents are behaving.
First of all, I should say that I'm not all that familiar with the latest work in that community, but I'm familiar with some papers, and it does definitely relate to this as well. I'm not sure, what kinds of methods they use. I think it's mostly based on you have pre-specified models, and they try to detect deviations from that, which in that sense relates to that as well. But so it definitely relates to it. But unfortunately, I can't go into detail because I'm not too familiar with the latest advancements there. Or if I can come back to your comment, one difference as well that I pointed out in the presentation is if you do model criticism in data fitting scenarios, then you don't have this online component. Whereas in the multi-agent systems setting, you have additional pressure or complexity coming from this idea that this is happening as you interact, as you collect the data. So you can't just reason about the correctness or do the model criticism in an isolation from the data generation process. Your reasoning will be part of the data generation process as well.
Well, but if it's just an abstract reinforcement learning setting, it's also true, right? Interacting online with unknown environment.
Yes, in the reinforcement learning because you interact with the environment. That's right.
When you combine many different tests, do you end up with just one p-value?
Yes, yeah. So the different score functions, they will be part of the overall test statistic.
But you just add them together?
Well, it's actually, and this method is relatively simple. So it's defined as the average of a weighted difference of the scores. So these are the different score functions, and you calculate the difference. And if you interpret this as a likelihood, they should be high, and this gives you the zero result. Then 0 is what you need to get a high p-value, and that's where the intuition comes from.
Wouldn't it be better to do many different tests and get many different p-values and see if more than the expected number of p-values were very low?
You mean you would you would basically just reduce this definition to one score function? Or
I would do many different score functions separately.
Could you do that? Well, I suppose you could do that, but then you would have I'm not sure if that would give you an edge over this.
You would need to compensate, because if you have a lot of statistics and one of them randomly, unlikely.
So
sure, but I just thought you could.
I'm not. You could surely. I think you could do this, but then I'm not sure if this gives you more power than this. And the other thing as well is, even if it does give you more power, then there's complexity issues as well. But if you do this simultaneously and it's independent, then maybe the increased complexity doesn't matter all that much.
So I guess the question is a weighted sum the right metric for this, or should it be some other LP norm or some other statistic of these?
I don't know. I don't know at this point. Yeah.
So how would this handle your example with the rock, paper, scissors, where the true world was a deterministic one, and maybe there the problem was the IID assumption there. But it seems like the natural kind of score functions kind of have the IID baked into it in the first place.
What do you mean the IID in the?
So which of the score of the test statistics that you have would detect
that you actually?
I see. So first of all, you would need to specify what model you do the test on. This is if you use the limit model here, say after maybe 1,000 interaction, and you do the test on this model, you would do a uniform test. For the first score function, it wouldn't help you because the first score function over a uniform one always gives you the highest score. But it does the third score function, which is the empirical average. Actually, the third function I think wouldn't capture that as well, because if you have the sequence, you get a uniform as well in the limit. So my guess would be that the second one captures it, but I would have to look more into the detail.
Maybe the second one?
The second example of the score functions here. I'm not entirely sure because I've not actually carried this out in my mind, but from what I can tell, the first two score functions actually wouldn't be able to solve that. Because in the limit, the sequence is uniform, and the limit model is uniform as well. So yeah, I'm guessing this guy would be able to provide the information, but I'm not sure, to be honest.
It seems like in order to solve this example, you need somehow to consider correlations between
yes,
not just each one separately.
You can, if you can definitely you can encode correlations as well in your score function, but these simple ones don't actually do that. One more note I should make here. This is a statistical test, and so if you end up with a deterministic distribution here, my personal recommendation would be to have some prior layer that tries to identify the deterministic relation, and then you don't actually have to go ahead and do all this relatively complicated testing, because then you only have ones and zeros. Then,
but I mean, you have some space of hypothesis, and you're sort of trying to find. You sort of found the best model out of the space of hypothesis, but basically what your test is trying to do is understand that maybe the truth is not even in the hypothesis space, right?
Oh,
you sort of cannot assume a priori that if you can identify the right thing, then everything is okay. The problem happens when you cannot identify the right thing.
This testing method does not reason about a space of hypotheses here. It's only yes or no that it delivers. Yeah, so the space of hypotheses would be some kind of model selection, which is what's happening here.
Yeah, but like, I mean, the reason that this is not good enough in some sense is because maybe the truth is not, like, if one of those models is the correct model, then a Bayesian agent will converge to the right model. But if the truth is not in the hypothesis space at all, then it will converge. Then your sort of method might, in principle, detect that something here is wrong.
Exactly. That's the idea. That's right.
So what is the null hypothesis here?
What is the what?
For the p-value, you need a null hypothesis here.
I need a what?
A null hypothesis.
Oh yeah, the null hypothesis, as for any p-test, is that the hypothesis is correct. Here. These two things are the same, and that's what allows you to specify the distribution over values here. So you have one common distribution over test statistics, basically. So think of the Gaussian in the limit, and then you calculate your test value. You take the spot, and then you just take the outside cumulative value.
This is in some sense the opposite of what is usually done in statistics. When you have a hypothesis, and you want to show that this is the correct hypothesis, not the null hypothesis. And here you're sort of trying to prove that the null hypothesis is correct. Right?
Well, I would say this in this particular, I guess you could say, standard way of calculating p-values, this is actually the normal thing to do. I think in the Neyman, Neyman something variant where you have two hypotheses, the H1 and the H0, then you have what you just described. Yeah.
All right, can we do one more question and then we'll have more discussion time?
Have you made any attempts to map this into a Bayesian framework and see what it ends up looking like in that context?
You mean such as maintaining beliefs over a set of alternative models?
Something like that.
Well, yeah, you can certainly combine these two things. First of all, if you reason over a hypothesis space, finite or uncountable, then this, as was just pointed out, and as I pointed out, this does not necessarily give you the true answer if the true behavior is outside the space. But you can combine these two things by maintaining your Bayesian belief and doing the testing simultaneously. And the testing may be able to tell you that this is no good at all. If it gives you a negative test result in the end. So then you can either change your hypothesis space, you can start learning based on different assumptions, or you can just scrap all of this and do some default policy, for example. On the other hand, if you mean combining or adding some Bayesian reasoning into the score functions, you can do that as well. Even though I haven't done it yet here because they're fairly simple, they don't do any Bayesian reasoning in here.
It seems like one place that it might be natural to use these conservative methods is in inverse reinforcement learning, when you're trying to learn the preferences of some human operator or whatever, and then it would be nice to have something that says, because you start with some prior and then you sort of update your beliefs, and then it would be nice to say something, well, your prior was actually not good somehow. The correct thing is not even in the space.
Yes.
Just shut down, don't do anything.
Exactly, yeah. Yeah, that was the idea behind this originally. But then, as I pointed out, this is ultimately just a small piece in the overall product that we want to achieve. Okay.
So let's thank Stefano again.
Thanks.